Okay, so is that clear? It's not clear, right? So exam 3 will be on Wednesday. '27. So 3/27, 2022. Was that?
You mean 4/3? You mean 4/3?
The April instead of March.
Oh, yeah.
4/27. Okay, so on the final exam, actually this is from 8 to 8:50. And our final exam will be Monday. 5th. And this one is at 7:30 to 9:30. Yeah. So much. Okay. So we will try to do. So what we're remaining with a very important section that we need to do is section 4, 4.4, chapter 5. I think we will do 5.1, 5.2, and 5.3. The 3 of them. So what we are remaining. So the other sections, if we get some time, we might go through some other sections. But the 4 sections. Okay, so your grade is out of 500. 500 points. 500 points. So the first exam is 400. Sorry, is 100. Exam 2 is 100. Exam 3 is 100. Final exam is 150, and then homework is 50. So this will be 500. So 500 points. So you might not know your grade up to this point. So you might know it at this point. So you will need to look for, you need to know how many points you need to get to get an A. To get an A, I think I gave it to you. I think it's 465 and above. Yeah, 465. So try 465 and above. Okay, any question? Any question?
Will you post those numbers in Moodle so that we can see the calculations, the test grades,
It is actually in our syllabus.
like what we got on those tests?
Oh, you want to know what you got in your test?
Yes.
So you want me to put it in Moodle or you want me to send it to you? Moodle? I don't try to put the exam grades in Moodle. If you want, I can put it. You want me to put it there? Appreciate that, yes. Okay, no worries. I'll put it. All right, any other questions? Good. Okay, let's continue from where we left, and we are looking at the basis. For vector spaces. Basis for vector spaces. And we'll start from definition 2.1. So what is a basis? So a basis for a non-zero vector space V is a subset beta of V such that, number one, the vectors in B are linearly independent. Number two, V is spanned by the vectors in B. That means every vector in V can be expressible as a linear combination of the vectors in B. So basis, we call it the beta. B is a subset which is in B. Such that one, it is linearly independent, and two, it actually spans B. It actually spans. So we know that we define the empty set to be the basis for S0 vector space. We define the empty set S. This is for the zero vector space. Example number 2 in this section. Example number 2. Show that B, which is the basis of V, is a basis for the given vector space. Number A. B equals to 1 t squared all the way to Tn in the polynomial which has 0 or real coefficients. With the real, show that is so this one is a basis for the given vector space. So this is a basis for the bigger polynomial, which is this P here. So we want to show that this one is actually in P. So how would we show that that is in P? So we need to check, first of all, number 1, whether it is linearly independent, and number 2, whether this B here and our V here is this P. So this is the bigger one, and this one is the subset of this. So we want to show, number 1, whether it's linearly independent, number 2, whether it spans the Pn, the Pn. So the solution. So number 1, we need to prove that P is linearly independent. It's linearly independent. So in this case, if C naught plus C1t plus C2t squared plus Ctn equals to 0, This is Cn, t equals to 0. Then for this one to be linearly independent, that means C naught equals to C1 equals to Cn equals to what? Equals to 0. So 1 t squared all the way to Tn are linearly independent. So that's the process. Now we need to check that this one now spans the bigger polynomial. So we need to check that. So number 2, if P of t, and this is P of t, is in Pn, which is the bigger polynomial, then there are C naught, C1, Cn, which are elements of real number, such that C naught times 1 plus C1t plus C1t squared C2 plus CNTN equals to PT equals to PT. Then therefore, then our B is a basis for P. Is. Now this P is in this. If this P is in this, then C naught and C1 are that. Then that means this P is a linear combination. So it is a linear combination. So therefore, it is a linear combination. Then it means it spans this B here spans. Example number 2, number B. B equals to P1 of T, P2 of T, P3 of T, and P4 of T in P3, where P1 of T equals to T minus 1, P2 of T equals to T plus 1, P3 of T equals to T squared minus T plus 1, and P4 of T equals to T cubed plus T. This is just similar to the example that we had, example number 1. Number 1A. So what did we find from example number 1A? So we found that solution. We found out that this is actually what? Linearly independent. So it is linearly independent. So that is the first proof that we got from number 1. So number 1, we proved in example 1A that P1 of T, P2 of T, P3 of T, and P4 of T are linearly independent. So we proved that they were linearly independent. So that is the first thing. Now we want to check whether this is. We want to check whether number 2. So we want to see whether this P of 3 is spanned by this beta now. So we want to check whether that this P of 3 is spanned by beta. So what do we do? So what we do is we let P of T to be an element of P3. So we can let P of T to be an element of P3. Now, since this is a polynomial of order 3, then P of T equals to A0 plus A1 of T plus A2 of T squared plus A3 of T cubed. So PT this P is equals to. Okay. P is equal to that. Then where A0, A1, A2, and A3 are elements of real number. Now we want to determine whether C1 of P1 of T plus C2 of P2 of T plus C3 of P3 of T plus C4 of P4 of T are actually equals to P of T. Equals to P of T has a solution or not as a solution. So what? So therefore, we know that C1 and P1 of T is this. P1 of T is T minus 1 plus C2 of T plus 1 plus C3 of T square minus T plus 1 plus C4 of T cube plus T and equals to, this is equals to A0 plus A1 of T plus A2 of T square plus A3 of T cube. So now we distribute the constant there, and then we collect the like terms. Then now those coefficients which we get from here, like the constant, are equals to the constant. If it is of order 2, then it's equals to 1. So, like what we did in example number 1. So what we got is C4 of T cube plus C3 of T square plus C1 plus C2 minus C3 plus C4 of T plus minus C1 plus C2 plus C3 equals to A3 T cube plus A2 T square plus A1 T plus A0. So we now have this equals to the. So now we now set the constant equals to the constant there. This equals to the other one like that. So we now start from this. So minus C1 plus C2 plus C3 equals to A0. And then we have the one for T is this. So C1 plus C2 minus C3 plus C4 equals to A1. And then for T square is C3 equals to A2. And then for C4 equals to A3. Okay. So we now form equations. Now we want to check whether these are giving us the solutions. Okay. So we now take the augmented matrix of this. So to take the augmented matrix here, so we pick the coefficient matrix first, and then we add the constants there. So -1 here is 1, 1, 0, and then A0, 1, 1, -1, 1, and then A1, and then we have 0, 0, 1, 0, and then A2, and then 0, 0, 0, 1, and then A3. So when we reduce nowadays, so when we reduce the matrix, so when we put this one to be 0, so it is the new R2 to be R2 plus R1, then what you get is negative 1, 1, 1, 0, A nodes. We get 0, 2, 0, 1, A nodes plus A1, and then 0, 0, 1, 0, A2, 0, 0, 0, 1, 0, A3. So what can so we can see that it is now, we can see that the linear system is consistent. It is consistent because we have the pivot positions in each of the rows or the columns. It is consistent. Then therefore, so our P of T is a linear combination of P1 of T, P2 of T, P3 of T, and P4 of T, and P4 of T. So that is how you check. First of all, you check the independence, and then the second one, you check the bigger polynomial. Okay, let's look at example number 3. Find a basis for the subspace V of R3 spanned by the vectors negative 2, 2, 3, negative 3, 4, negative 6, 8, negative 2, negative 3, 2, negative 4, 1, negative 3. Find the basis for the subspace of V. So how can we find this? So what is the solution? So in this case, we should note that V is equals to the column space of A. So to get this, the subspace V, that A is the same as getting the column space. And we say the column space of A is found when we use this matrix. And the vectors which are giving us the pivot position are the ones which are in column space of A. So here now, we write this matrix, we put this matrix as A to be equals to, in a matrix form, negative 2, 2, negative 3, 4, negative 6, 8, -2, -3, 2, and then -4, 1, and -3. So we put that in. Then when we reduce this matrix, I already reduced this, then what you get is 1, -2, 1, 2, 0, -2, -5, -3, and then 0, 0, 0, and 0. So that is what we will get once we reduce. So reduce to H log. Oh. So we get that. So the vector which has the vectors which have the pivot positions are this and this. So those are the two vectors which have the pivot positions. So therefore, so our B, which is the subspace there, is equals to the span of this vector here, -2, 2, and -3, and 4, -6, and 8. Those are like that. So this is a basis for 2. So it's a basis. Okay, let's look at the last section in this, the last subsection in this section, number 3. We call it the spanning set theorem. The spanning set theorem. Three 3.1 and this one is here, 3.1. If we let V be a vector space and H be the subspace of V spanned by S equals to V1, V2, all the way to VP. If we let V to be the vector space of and H be the subspace of V spanned by S, which is equals to those vectors there. Then number 1, if some vector Vk, if some vector Vk is a linear combination of other vectors in S, then H equals to the span of V1, V2, Vk minus 1, and then Vk plus 1, and then continue like that to Vp. So since Vk is a linear combination, of the vectors which are in this S, then our H now will be the span of the remaining vectors. The remaining vectors, which is not including. Number two, the set S contains a basis of H. The set S contains a basis of H. Okay, so this is the spanning set here. So there is some harmonic vector which is ES with a combination of the vector, then H will be this. And finally the set S contains basis of H. So we will prove all this. So let us prove this. So first of all, we need to prove that H is equal to W. So we want to see something here. So what we need to do is, first of all, we can, so we look at the proof. So number one, suppose that Vk equals to C1 V1 plus C2 V2 plus Ck minus 1 Vk minus 1 plus Ck plus 1 Vk plus 1 plus Cp Vp. Suppose that Vk is equal to that. Where C1, C2, all the way to Ck minus 1, Ck plus 1, all the way to Cp are elements of real number. Elements of real number. Then we can define W to be equals to the span of now these vectors of V1 all the way to Vk minus 1, Vk plus 1, all the way to Vp. We can define W will be the span of that. So what we need to do is we need to show that W is equals to H. So we want to show that W is equal to H. We want to show that W is equal to H. So then our W equals to A1 V1 plus AK minus 1 Vk minus 1 plus AK plus 1 Vk plus 1 plus AK AP Cp AP Vp here Vp say that A1 A2 AK minus 1 AK plus 1 all the way to AP are elements of real number. So let's let W to be that. Then also this W is also equals to A1 V1 plus AK minus 1 VK minus 1 plus 0 VK plus VK or AK plus 1 VK plus 1 plus AP VP such that A1 all the way to AK minus 1, AK plus 1, all the way to AP are elements of real number. Elements of real number. So this can also be written where the VK is actually 0 in that case. So therefore, if we have written like that, then that means this is in what? So this is actually in H. This is in H. Because we say our H is the span of this. So our H is the span. So that is in H. Okay. So that we actually write like this. So this is a subset. So that is in H. Now, if V is an element of H, now if V is in H, now if V is in H, then there exists A1 all the way to AK minus 1, AK plus 1, plus, sorry, all the way to AP, which are elements of real number. If V is an element of H, then there exists A1, also including AK, such that V is now a linear combination of A1 V1 plus AK minus 1 VK minus 1 plus AK VK plus AK plus 1 VK plus 1 plus AP VP. Now these are vectors. All these are vectors. Now we say that VK is a linear combination of, and we say that then also this is equals to A1 V1 plus AK minus 1 VK minus 1 plus AK, and then we say that VK is a linear combination of the vectors in S, and this VK is equals to C1 V1 plus CK minus 1 VK minus 1 plus CK plus 1 VK plus 1 plus CP VP, and then plus the one AK plus 1 VK plus 1 plus, so that is closed, plus the last one, which is AK, and then AP, and then VP, AP, and then VP. And then basically this is in what? So basically this is in, this is in. So when we open these brackets, so it is the same as A1, and we collect the like terms, AK C1, and then B1 plus AK minus 1 plus AK CK minus 1 plus AP plus AK CP VP, and this is in W. This is in W. So therefore, then H is a subset of W. And then if this W is a subset of H and H is a subset of W, then H is equal to W. So if you do some theoretical maths, so these are the things that you should do. So you prove a lot of theorems. Right? You know, like theorems, right? So these are the things which most of the time. Okay. Now, number 2, we want to see if the S contains a basis of H. Contains the basis of H. So number 2, if the vectors in S are linearly independent, then S is a basis for H. If the vectors in S are linearly independent, then S is a basis for H. Otherwise, we can delete a vector from S which is expressible as a linear combination of other vectors in S and denotes the new subset of V by S1. We have span S1 to be equal to the span of S. So if we repeat this process, and after M steps, the vectors in SM are linearly independent. Since span of SM equals to span of SM minus 1 equals to span of S1 equals to span of S equals to H. The set SM is a basis for H. So what do we do here? So like what we just done in section 1, V1 was a basis in S, right? So we actually deleted V1, and then now V1 is a span of what is remaining. Now, when we delete again, the next one, V2, Then the remaining ones will span. Okay. So when you continue like that, so you realize that they are linearly independent, and actually those are the basis of the page. So they are the page. So you can delete and delete up to the last one. And then it will still be the basis of H. Okay, so an example is the one which you did in section example 1, the last one, which we can put P4 to be equals to P1, P2, and P3. So we'll see on that when we meet on Wednesday. Okay, I'll post these notes in Moodle.